Sorry, this is part 2. I had to replace the battery in my pen. So I was talking about the 5 different types of gas problems that you'll encounter, and the first one is single variable problems. The 3 steps that you follow, you're going to use for each type of problem. So an example of a single variable problem you might encounter would be something like this. What is the volume of 2.0 moles of nitrogen gas at 3.5 atmosphere and 385 Kelvin? So the only thing that's missing is volume. We want to know what the volume is. I've given you everything else. So step 1, we're going to rearrange the ideal gas law equation so that we are set up to find volume. We have PV equals nRT. And in order to get volume by itself, we're going to want to divide by pressure on both sides. So pressure, where did I make that? So I'm going to use a blue. So if I divide by pressure on both sides, that means on the right side I can cancel the pressures and I am left with volume, and that's going to equal nRT over P, over pressure. We have N R T, and all of that is divided by pressure now. Alright, so we are set up to find volume from our equation. So now let's look at number 2. We need to check the units to make sure they agree with the R constant. We are given from the problem itself moles, 2.0 moles. We are given 3.5 atmosphere, which is pressure. And we're given 385 Kelvin, which is temperature. We don't know the volume, and we want the volume in liters. R is, in terms of units, we just calculated it, atmosphere liters per mole Kelvin. We have moles, we've got a atmosphere, and pressures in atmosphere, we have temperature in Kelvin, and we're looking for liters. So we have all the correct units, and we can just plug and chug now. We'll put everything into our rearranged equation so that I get the volume out. So I have volume is equal to 2.0. Please write the zeros, because remember these are trailing zeros and they are now significant. Times our gas constant, which we've calculated to be 0.0821. You're going to use this value at all times. Make that pink. 0.0821 atmosphere liters over mole Kelvin. Multiply that by temperature, which is 385 K, and divide all of this by the pressure, which is 3.5 atmosphere. Moles on denominator or numerator here denominator here cancel. Kelvin on the bottom here, they're on the top in temperature. Those cancel. The atmosphere, everything's divided by atmosphere, which is the same thing as saying times 1 over 3.5 atmosphere. So these cancel. And if we follow the math and go to the correct number of sig figs based on rounding rules, you should get 18.062 and a bunch of other numbers, but we're rounding and we're going by least number of sig figs, which is 2 from the moles and from the atmospheres. So we should report it as 18 liters of nitrogen gas. And that is a single variable problem. So now if you pause the video, take a second and work on this problem on your own, and then you can continue the video and see how I work through it. We're going to follow those same 3 steps. Step 1, rearrange our equation for what we're looking for. In this problem, we have 25 grams of oxygen, and that's put into 0.750 liter container at 25 degrees Celsius. And we want to know what is the pressure. So we have our initial equation, PV equals nRT. You don't have to write this in different colors all the time. I just am doing it to make it clear that these are all different units. But if this takes too long for you, just use the same color. I want pressure by itself. In order to get that, I have to divide by volume. That's going to cancel it on the right side and move it over to the left side. And that's going to give me pressure is equal to moles times the gas constant times temperature divided by volume. Alright, let's check our units of what we're given, see if it matches with the gas constant R. So what we have, let's do check units with R. So we're going to do what we have, what we want. So we know we want pressure in the units of ATM. Remember, it's according to R. And then R, which we know the units, atmosphere, liters, over mole, Kelvin. Alright, so what we are given. Our volume is given in liters, so that checks out, 0.75 liters. Cool. Our temperature is given in degrees Celsius. That does not check out with R. It should be in Kelvin. To get to Kelvin, we have to add 273.15 K. And again, we're only going to round to the ones place because we are adding. And we should get 298 Kelvin. And then, what about moles? So now our Kelvin, our temperatures match. We don't know the pressure, so that's our unknown. But how can we get moles? There's no moles in this equation. The trick in this case for moles is what relates grams to moles? It's molar mass. So we have 25 grams of oxygen. And we'll do light blue. We're given 25 grams. The molar mass of O2 is 31.9988 grams of O2 for every mole of O2. And that gives us, if we are rounding to correct sig figs, which is 2, 0.78 moles of O2. Now we have moles. And now we can just plug everything into the equation and calculate it. So you do plug and chug or substitute and solve, whatever helps you remember it. And we've got pressure equals moles that we just calculated from the given grams using the molar mass conversion, times R, which is always a given. It's going to stay the same always and forever in the ideal gas law equation. Write out all those units, liters, moles, Kelvin, multiplied by temperature, and that we calculated to be 298 Kelvin. Divide everything by the given volume, which was 0.750 liters. And if you calculate that with your calculator and then you follow sig fig rules, two significant figures from the moles, you should get some number. Let's see, I got 25.44 ATM, but I gotta round it to the correct sig figs, which is just 25 atmosphere of, what was it, oxygen. Alright, so that is type 1. Type 2 is calculating the density of a gas. It's kind of like a single variable problem, but there's 2 steps. So way back in, what was it, chapter 2, we talked about density. And if you remember, if you want to pause the video, write down what density equals from what you remember. But density is, what color do I use? Okay, of the mass divided by the volume of something. So, we've got 2 unknowns currently. So we want to know, what is the density of argon at 15 degrees Celsius and 1 ATM? Well, mass we could figure out using the molar mass, because the molar mass of argon we just get from the periodic table. It's some number of grams divided by moles of argon. But in this problem, we're not given how many moles of argon we're working with. So in this case, whenever you aren't given the number of moles, just assume it's 1 mole. It makes your life easier. 1 mole of argon is going to weigh whatever the grams are on the periodic table. The volume, though, has to come from the ideal gas equation. So to solve this problem, we got to set up our equation for volume, divide each side by pressure. That gives us volume equals moles times the gas constant times temperature, all divided by pressure. Then we solve like we do usually for the ideal gas equation for volume. So we are given temperature at 15 degrees Celsius, but remember our temperature should be in Kelvin. So we have to use that conversion. 15 degrees Celsius plus 273.15 Kelvin gives us 288 Kelvin after we convert it. We're also given atmosphere, so the pressure is in the correct units. We're good on pressure. Now we're good on Kelvin because we converted it from Celsius. And we're assuming 1 mole. 1 mole, because it wasn't stated. And we want to know the volume. So we need to find V in liters. We don't know volume. So now we can plug and chug because we have all of the pieces. So we've got volume is equal to, we assumed 1 mole times 0.0821 atmosphere liters moles Kelvin times temperature 288 Kelvin, all of that divided by the pressure, which was 1.2 atm. Moles cancel, Kelvins cancel, atm cancel, and I get, after the calculation, 2.027 grams per liter. Oh, getting ahead of myself. Hold on, I skipped a step. I get 19.704 liters. So that's the volume right there. If I look at the periodic table, I will see that the molar mass of argon is 39.948 grams. It's grams per mole, but I only have 1 mole, so the moles would cancel and I'm left with grams. If you don't believe me, do that calculation. And I divide that by the volume I just calculated, 19.704 liters. Grams over liters gives me density, which is what I wanted to find originally anyways. And if I divide that, I should get 2.027 grams per liter. You round it. So remember, from this whole equation, 2 sig figs. So I should be rounding here, but I rounded the last step, and I end up with 2.0 grams per liter, which is the density of argon in this scenario. So now you try it for 2 gases. What are the densities of helium and CO2 in each of these balloons? The conditions are the same for each balloon. The temperature is 22.00 degrees Celsius and the pressure is 755.0 millimeters of mercury. So remember that SI unit that I want you guys to know? That comes into play here. You might need an extra sheet of paper. If you do, feel free to use one. I'm just going to draw on the slide, so I don't need this extra slide, but you might need an extra piece of paper. So pause the video now if you'd like to try this yourself. I highly recommend you do. You're going to follow the same 3 steps. So step 1, rearrange the gas equation. So again, we want density, which is mass over volume. And the volume is what comes from the rearranged gas law equation. And if I rearrange this for volume, you have to divide on both sides by pressure. You don't have to do this step every time if you've already, you could do it in your head, that's fine. I'm just reiterating it because it can get a little overwhelming. I get overwhelmed with word problems, so I'm just showing each step as we go to reiterate that they're going to look pretty similar. And then we're going to divide by pressure. This is what we're going to use. Alright, step 2. We're checking units with R. We need to write down what we have, what we want, and we actually need to write down R. Units of R are atmosphere, liters, moles per mole Kelvin. So what are we given in this problem? We've got temperature, 22.00. A little bit different sig figs this time. If I add that to 273.15 Kelvin, both Celsius and Kelvin have 4 sig figs, so we get 295.2. Using the wrong color. It should be red for Kelvin. 22.00 degrees Celsius to Kelvin. So I'm adding that 273.15, and that is 295.2 Kelvin. We're also given pressure in millimeters of mercury. And if you go way back, alright, not that far back. Page 2, SI units, 1 atmosphere equals 760 millimeters of mercury. So for the pressure, we have 755.0, 760 millimeters of mercury on the bottom, so I want those to cancel for every 1 atmosphere. And that's going to give you, again, to proper sig figs, which is 0.993 atmosphere. So we've got atmosphere now after conversion, Kelvin after the conversion. Now moles. Notice there's no grams. We don't know how many grams of the gas is. So again, if we don't know the grams or the moles aren't given, just assume 1 mole. We've got 1 mole of each. So all these things are going to be the same for both. And if we're assuming 1 mole, and we know that we want the volume in liters. We can now go on to step 3, which is substitute and solve. There's a couple of substitutions happening. First one, we're just going to do the gas law. We got 1 mole times 0.0821 atmosphere liters mole Kelvin times 295.2 Kelvin, all of that divided by 0.993 atmosphere. And that gives us the volume of gases under these conditions, which is 24.4 liters. Lowest sig figs, 1 atm. The 0.993 atm. Moles, exact number. We're assuming it's exactly 1. So to 3 sig figs, now we can just calculate the grams of each using the molar masses, which you guys have done many times before. So if we're assuming 1 mole of helium, I'm just going to look at the periodic table, and helium would give me 4.00260 grams. I divide that by 24.4 liters, and that gives me 0.164 grams per liter helium. For CO2, if I calculate the molar mass, that's 44.010 grams. Divide that by the liters that I just calculated from the ideal gas equation, and that gives me 1.080 grams per liter CO2. And that is the end of this question. Calculated the volume of each of the gases in each of the balloons. This question, why is CO2 lower than the helium when the pressure and temperature are the same? So the density of air in the room is 1.3 grams. So that's all the air all around here. So why would a helium balloon float and CO2 balloon would not? Well, if we compare the density of air, 1.3 grams per liter, compared to helium, which is 0.64 grams per liter, helium is lighter than air, so it would sit on top of the air. That's why the balloon floats. Carbon dioxide, though, is 1.80 grams per liter. It is heavier than the air, and therefore shall sink to the floor. It's trying to get underneath the air molecules because they're heavier. So comparing densities lets you figure out how different gases will stack on top of each other. So now we can move on to type 3, which is figuring out the molar mass of a gas. It's a little bit different than what you guys have seen so far with molar masses, because you have to use the ideal gas equation. So a type of problem like that would look something like this. 1.92 grams of a gas has a volume of 673 milliliters at 0 degrees Celsius and 1 atm. What is the molar mass of the gas? Well, we know molar mass, grams per mole. So this is going to come from the ideal gas law now. We're not going to use the periodic table. Same 3 steps. You're going to rearrange your unknown. We're trying to find the moles, so I have to divide by RT on both sides. That gives us N, which is moles, equals all of this. So now we're going to check our units against R, atmosphere liters per mole Kelvin. We are given volume 673 milliliters, but we need liters. If we want to convert from liters to milliliters, 673 milliliters, that M We've got milliliters stands for 10 to the minus 3 liters. And that should give you 0.673 liters. We're also given pressure, so we've now converted to proper volume units. Our pressure is already in proper units. We're good to go. We don't know the moles, that's what we're looking for. And our temperature is given in Celsius. Got to convert that, add 273.15 to that, and you should get 273 K, following proper units. Now we can go on to step 3, which is just plug all of that into our rearranged equation, and that is going to give us N equals our pressure times our volume. Don't forget to write your trailing zeros. They matter when you try and figure out significant figures. Divide all of that by R, which is atmosphere, liters, moles, Kelvin. And then also on the denominator is 273 Kelvin. Kelvins cancel. Liters are numerator down here, which means if I were to bring them up here, they'd flip, be on the denominator, so these cancel. Moles are denominator. Oops, we want moles. But if I brought it up here, they'd flip, so it'd be on the numerator. And same with ATM, they would flip, so those cancel. If I calculate this, I end up with 0.0300 moles. Remember, we want the molar mass, and so we use that. We were given 1.92 grams of this gas. I'm going to divide that by the moles that we just calculated. So 3 sig figs in our moles from the 3 sig figs in this equation. 3 sig figs between each of these, so I need to report my answer to 3 significant figures. We don't know what kind of gas it is, so I can't say, but that is the density, or the molar mass, sorry, of the gas. So now you can pause the video, try and do this problem, and then you can continue the video, and I will work it out, and you can follow along. So for this problem, a gas has a mass of 0.125 grams and a volume of 0.100 liters at 0.728 atmosphere and 25 degrees Celsius. What is the molar mass? So we know a molar mass is equal to grams per mole. We need to find moles using the ideal gas equation, just like we did in the previous example. And we know to do that, that N has to equal the pressure times the volume, all of that divided by R times temperature. You then want to check the units against R. So we have what do we want, and what is R? R is ATM liters mole Kelvin. We want to find N in moles, so we don't know that. So we should be given everything else. In this problem, we have volume, again in the correct liter units. Don't forget to write your trailing zeros, so that checks out. We're given the pressure, also in the correct units. It's nice when this happens. And the temperature is not in the correct units. We have Celsius, so we gotta add. And if we add, we get 298 Kelvin. All right, now we can plug and chug. So step 3. So this is to solve for moles, and then use that to solve for the molar mass. Okay, so we get everything that we just figured out, or were given. So we're given the pressure, didn't have to do any conversions. We were given the volume without converting. It should be liters. We are always given the gas constant. And then we had to convert temperature to 298 Kelvin. Kelvins cancel, ATM cancel, and liters cancel. And that leaves us with 0.0728. So I'm going to actually show you, I'm going to do this a different way. I'm going to show you, since I have space, how these units can cancel, in case you've forgotten how dividing by fractions of units work. So I'm going to just multiply the numbers on the top. I'm going to get 0.0728, and that's ATM times liters up here. And then I'm going to just multiply through the denominator numbers, and I get 24.4658. Now I'm going to keep track of sig figs. I have 3 here, 3 here, 3 here, and 3 here. So I should be having 3 significant figures at the very end. Now the units down here, the only thing that cancels is Kelvin. So I'm left with ATM liters divided by moles. And now I'm just going to separate this fraction out. 0.0728 the ATM liters stays on top with that number, and then we have times. Okay, so we got this number, 24.4658, attached to atmosphere liters, and the moles is just 1. We don't write the 1, but it's there. So I'm going to write 1 mole up here. So the moles are now the numerator, and on the bottom we have this 24.4658 atmosphere liters. This is an algebraic property. You can look it up. But I'm just trying to show you this is why we can cancel atmospheres and liters when we're up here. If you do this math rounding to 3 significant figures, you should get this number. And then again, we're trying to find molar mass. We're given 0.125 grams divided by the moles that we just calculated, and that will give us grams per mole, which are the correct units of molar mass. And again, 3 significant figures here. And you've solved this problem. All right, 3 down, 2 to go. Type 4, change in conditions. So this is the one where there's quite a bit of information to keep track of. We'll get to that in a second. First, let's just read through this problem. So a weather balloon has a volume of 50 liters. That decimal place tells you 2 significant figures at 1.0 atmosphere and 22 degrees Celsius. The balloon rises to an altitude where the pressure is now 0.050 atmosphere and the temperature is now negative 50 degrees Celsius. What is the volume after the balloon rises? So in this case, we have 2 conditions. Initial conditions, which are given in the first sentence, and then final conditions, which are given in the second sentence. So when we rearrange our ideal gas law in this case, we have more than one variable. More than one thing is changing. The only thing that's constant is your constant gas variable, your R constant. So in this case, R doesn't have a subscript because it is the same. So we can define these initial conditions as P1, V1, initial pressure and volume, is equal to the initial number of moles times the gas constant times the initial temperature. And then you define your final conditions just with different subscripts. But R doesn't get subscripts because it is the same always and forever. Because R is the same, if I solve for R on both sides, in each of these equations, I get that no matter whether I'm looking at the initial condition or the final condition, R is always going to equal this set of values. Since R equals both things, that means that I can set these equal to each other. The initial conditions have to equal the final conditions. You can kind of think of it like a ratio. As one of these things change, everything else has to change accordingly. So we already talked about how these were related to each other. So you're going to use this equation. Again, it's still a rearrangement of the gas law equation. We just have 2 different sets of conditions, and we're setting them equal to each other because R remains the same. You're going to use this equation for change in condition problems. Okay, so we've rearranged our equation in looks like a pretty drastic way, but these are the same ideal gas law equations. We just have two of them set equal to each other. So now we're going to check our units. We have to check our units for each of the cases. Oh, there's a little typo. There should be V2 and N2. So in the initial conditions, we're given 1.0 atmosphere, 50 period liters for volume. There's no stated moles, so again, we assume 1 mole. And then we're given 22 degrees Celsius, so we gotta convert that to 295 Kelvin. Final conditions after the balloon rises, we've got a pressure of 0.050 atmosphere. The volume is the thing we're looking for. Some number of liters. The moles, there was no mention that the moles changed, so they should still be 1 mole based on our assumption. And then the temperature changed to negative 50 degrees Celsius. If we add 273.15 Kelvin to that, we should get 223 Kelvin as our answer for temperature in the final conditions. Well, now we can take all of this data, plug it into our equation, and solve. So based on, let's look at the changes. So we went from 1 atmosphere to 0.05 atmosphere. So our pressure went down. If our pressure went down and our temperature went from 295 Kelvin to 223, what happened to the volume? What do you guys predict? Take a second, write that down on your paper. Does it go up or down for the volume? Remembering those relationships between pressure and temperature, pressure and volume, and all of those things. This is where that comes into play. You can even look at this equation. So as pressure decreases, what's going to happen to your volume? Alright, if I substitute this into that lovely new equation, P1, P2 times V2, whoops, that's V1, 1 of V2, and each of those divided by N1, N2, and temperature. 1, temperature 2, and they are set equal to each other. Put in the information that I have. So I have 1.0 atmosphere times 50 dot, don't forget that dot, liters, divided by 1 mole. This is the initial times 295 Kelvin. Move this down here so it's all lined up with the initial on the equation. And all of that is equal to the final pressure, which is 0.050 atm. We're solving for the volume. The moles stayed the same. There was no indication that they changed. The temperature, however, dropped to 223 Kelvin. But do some maths. I should get something. Alright, so I'm going to do the math on each side. So I'm going to do 50 divided by 295 Kelvin. That leaves me with 0.17 atmosphere. None of these units cancel yet. Liters over mole Kelvin. Oh man, atmosphere, liters, mole, Kelvin. Does that look familiar? And again, it's 2 sig figs, because that's 2 sig figs, and that's 2 sig figs. And then if I calculate on this side, I am left with 0.050 divided by 223 Kelvin. So here I am left with, let's sum this out, .00022 atmosphere over mole Kelvin. And the V2 is still there. If I multiply through by this whole thing, I shall be left with, just going to put it on the right side, 0.17 atm liters not multiply, dividing. So yeah, atm liters divided by mole K. All of that divided by this whole thing. Which is the same as saying divided by mole K times mole K over 0.00022 atmosphere. Atmospheres cancel, Kelvin cancel, moles cancel, and I'm left with 0.17 liters no, what am I saying? It's that divided by 0.22 and that should give you 772.72 liters, which if you round to 2 significant figures gives you 770 liters. This type of problem would probably be a challenge question on an exam. I will not be quizzing you on this. You might have homework, but this would be a challenge question. Again, if you're going into Chem 120 and you have questions about this, let me know. You will see this again in Chem 120. But you're not expected to memorize everything from this semester. Just being comfortable with manipulating the equations. So we're going to go on to type 5, the last type, stoichiometry of gas molecules. You guys did this already in your lab. You've done stoichiometry a bunch. It's taking a balanced chemical equation and going from moles of something to moles of something else. So in chapter 9, you learned conversions. You already knew grams to moles, which is you learned molar mass to convert from grams to moles, Avogadro's number to convert from moles to atoms, and then the balanced chemical equation helped you convert from moles of something to moles of something else. Chapter 11 is now going to allow you to go from liters, so the volume of a gas, use the ideal gas equation to get the moles of the gas, and then you can put that into the balanced chemical equation. So, same things we've been using throughout this whole chapter, but now we're going to apply it to a balanced chemical equation. So in this example problem, we have an airbag. An airbag is deployed by the following chemical reaction. Hopefully nobody's been in a car accident. I was, and the airbags deployed, and I didn't know how airbags worked at the time, and so I thought that all of the powder in my car was smoke and was freaking out that it was going to explode. It's pretty bad. I was rear-ended twice, and it sucked. But I found out much later that it wasn't going to explode, and that powder was actually from the airbag itself. So the way airbags work, they have sodium azide solid in them, and at 75 degrees Celsius and 1.2 atm, or you can just increase the pressure and not have that high of a temperature, it will undergo a chemical reaction and give you sodium solid and nitrogen gas. And so the airbag fills with nitrogen gas, and that's what protects you from getting concussions or worse in a car crash. The sodium solid is that white powder. Comes out. But anyways, moving away from the interesting inner workings of your airbags, knowing this balanced chemical equation, we could figure out this problem. Again, using the same steps. So I'm going to check if your chemical equation is balanced. If not, then balance it. You're going to convert normally. So here we have solids, so we're just going to go grams to moles, and then moles of reactant to moles of product. And you convert like that normally, quote unquote, until you get to the volume of a gas, or you have to convert from moles of a gas to volume. And then you're going to use the ideal gas law to do those conversions. So in this problem, we've got 25.0 grams of sodium azide solid are used to fill an airbag. So we want to know how many liters of nitrogen gas would be produced, theoretically, so theoretical yield again, during the deployment of this airbag. Well, we're starting with a solid, so we can just do the regular conversion using molar mass. The molar mass of sodium azide, if I calculate it from the periodic table, is 65.0099 grams. That's got to be on the bottom. And the moles per 1 mole goes on top. Alright, I got moles of my reactant, but we're trying to find the mass of our product. Well, we got to use the mole conversions from the balanced chemical equation. Let's double check if this is balanced. I got 1 sodium on the reactant side and 1 on the product side, 3 nitrogen on the reaction side, and 2 nitrogen on the product side. So we have to balance this equation first. If I put a 3 here and a 2 here, that gives me 6 nitrogen and 6 nitrogen. Those are balanced. But now I have 2 sodium and only 1 sodium. I'm going to put a 2 right there. Now I have a balanced chemical equation and I can proceed without worry. So if I want to convert from moles of my reactant, sodium azide, 2 moles of N2 gas, well, for every 2 moles of my sodium azide, I get 3 moles of nitrogen gas. If I do this math, and I cancel out the units, double checking, grams cancel, cool. Moles of reactant cancel, I'm left with moles of product, and that is what I want for the nitrogen. And I get 0.577 moles, theoretically. Alright, cool. I got moles of a gas. Well now, since I have moles of a gas, I can't use the periodic table conversion to get to grams. I have to use the ideal gas law. So we're going to go through those steps. Step 1, rearrange. For rearranging, we want to know how many liters of this gas. I have moles. I'm also given some other information. But first, let's just solve for volume. So PV, let me do this so I don't take up extra space. We're going to do step 1. Solving for volume, we're going to got to divide by pressure. That leaves volume by itself and everything else on the other side. Moles, gas constant, temperature, and pressure on the bottom. Cool. Step 2. What do we have? What do we want? And what is R? Does what we have match up with R? We know R is atmospheric liters per mole Kelvin. We want to know what the volume of the nitrogen gas is in liters. We just calculated our theoretical yield in moles. 7 moles. Got moles. If I look up at the chemical reaction, I see that I know what the pressure was at the time that this reaction would take place. So I have 1.2 atmosphere. That really checks out. The temperature I need to convert into Kelvin, and that would be 348. Step 3, substitute and solve. So I want to know the volume. I have the moles. I know the gas constant. Move this over a little. My gas constant, 0.0821. Atmosphere, liters, mole, Kelvin. Times temperature, which I calculated to be 348 Kelvin, and divide all of that by 1.2 atmosphere. Following proper sig fig rounding rules, I see that the lowest number is 2 sig figs, so I report my answer to 14 liters of N2 gas will be produced from this reaction. Alright, try this problem. This will definitely probably be on the exam. You also did a lab on this. It will be on the quiz. For sure. It shall be on the exam. Yes. Pause the video. Try it yourself, and then follow along. Butane, C4H10 gas, reacts with oxygen to make water, liquid water, and CO2 gas. How many liters of CO2 gas are produced at 1 atm at 125 degrees Celsius? If you start with 1 liter of C4H10 butane gas at 4.0 atmosphere and 25 degrees Celsius. Reacts is the key word here. It means stoichiometry. This is not a change in conditions problem. If you remember the change in conditions problem, we were talking about the change of conditions around the same type of gas. Physical changes. Stoichiometry, we're saying there's a chemical reaction taking place. Not only have the conditions changed, but the type of gas has changed. So this is a two-part problem. Where we're given, so let's first, we know it's a reaction, let's write out the balanced chemical equation. That would be step 1. Right, remember we need balanced chemical equation. We have C4H10 gas plus O2 gas reacts together, and you get liquid water plus CO2 gas. If you've already balanced this equation, great. If you haven't, please do so. If you have questions on how to balance it, let me know. The coefficients should be 2 moles of butane, 13 moles of oxygen, and 10 moles of water, and 8 moles of carbon dioxide. And we're only worrying about butane and carbon dioxide. So we know that butane, we started with 1.0 liters of butane at 25 degrees Celsius and 4.0 atm. We ended up with some number of liters of carbon dioxide at 125 degrees Celsius and 1.0 atm. I just got these lists from the word problem, so the information given. If we remember our steps for stoichiometry gas problems, right, we did the chemical equation, we balanced it. You convert normally until you're asked to find volumes of gas or convert moles of gas to volume. Well, right off the bat, we've got volume of our starting material. The balanced chemical equation can only accept moles, so we have to convert the volume given of butane into moles. So we need moles, and that's going to be pressure times volume divided by the gas constant times temperature. Step 2, check our units with R. So we know R is ATM liters, mole Kelvin. Again, as you get comfortable with this, you might be able to do this conversion in your head, or the rearrangement, like I did. I just set up the one I needed, and you might be able to figure out what you want and what you have already, but it's always a good practice to check it against the units. Because the most common error, especially when you're rushing, is dividing things incorrectly or multiplying them incorrectly because you're not keeping track of your units. So we want to figure out the moles of butane. C4H10. We are given volume, in the correct units. We're given temperature in the incorrect units. So if I convert that, I get 298. And we're given pressure in the correct units. If I substitute and solve, I get N equals 4.0 ATM times 1.0 liters. All of that divided by 298 Kelvin. Times the gas constant, which is 0.0821 ATM liters over mole Kelvin. ATM cancel, liters cancel, Kelvins cancel, and left with moles, which will flip up to the top after divide everything. And I get 0.16 moles of C4H10. Let's do it this way. So now I'm going to I have moles of reactant. To get from moles of reactant to moles of product, I have to use the balanced chemical equation. Moles of reactant, for every 2 moles of C4H10, I get out 8 moles of CO2. If I do that, that gives me 0.64 moles of CO2. Now I'm going from moles to liters. I have to use the ideal gas equation again, but now for CO2. I need to solve it for volume. So I have moles of CO2. I am looking for liters of my product. So if I rearrange the chemical equation, PV equals nRT for volume now, I get volume equals N R T and divide that by the pressure. Alright, step 2. Let's check the units of what I'm given versus what I want to have compared with my gas constant. So what do we have, what do we want, and what is R? We know R is atmosphere, liters per mole, Kelvin. We want the volume of CO2 in liters. We have the 0.64 moles that we just calculated. We have 1.0 atmosphere, it's given in the word problem. And then we have 125 degrees Celsius, which I need to convert into Kelvin. And that turns out to be 398 Kelvin. And now I can just plug all that in to my rearranged equation and solve for volume. 0.64 moles times 0.0821 atmosphere liters mole Kelvin times the temperature 398 Kelvin, all of that divided by the pressure, which is 1.0 atmosphere. Atmospheres will cancel. I need liters, Kelvin cancel, moles cancel. So our volume is equal to 21 liters of CO2 produced. Alright, that is chapter 11. Take your time when you watch this video. Again, you don't have to know all of this before Tuesday, but I want you to go through this and just write down, follow along, practice the problems, and write down anything that is confusing. Make note of it so that you can ask me in class on Tuesday when you will have time to ask me those questions and also work on your homework so you get more practice. Hopefully, by the end of this lecture, you got really annoyed of me saying the units of R because you knew them already, and you were more comfortable with rearranging the equation. This is what I mean by memorizing by doing. You don't just sit there and stare at the page hoping that you will just automatically remember it. You just do it so much that you know it. It also becomes muscle memory a little bit, but you just practice it so many times that you can write out the units of R. You start to know what R is because you've written it so many times, and that way you don't have to flip back and forth with the reference sheet a million times during the exam. Alright, cool. I will see you guys Tuesday.